Hello everybody. Since we have the lab this week, which means I can only have one actual lesson, the lab taking up our second meeting, I decided to put the second half of this lesson on Canvas for you. Luckily, the vast majority of this is review material and should be terms that you've heard before. If not, though, it's good to fill in the gaps and make sure that we're all at the same point. So we're going to talk a little bit more about states of matter, which I previewed a little bit in Monday's class. We're going to start by following along with the concept of heat. Right, so heat we talked about a little bit, like heating things up or losing heat. We talk about that sometimes as well. Heat is also known as thermal energy, but in particular, thermal energy is contained within something. So like I have thermal energy in my body. It becomes heat when it moves from one place to another, or when it is transferred from one location to another. Right, and so I have thermal energy in my body, the heat that is the energy, not heat, the energy that is retained by the particles in their movement. And then if the energy leaves my body, it becomes heat. I lose heat from my body. A very fine shade of meaning between the two, but I wanted to make sure that you understood that. So for example, during our lab, when we use a hot plate to heat up a beaker full of water, right, then the thermal energy flows from the hot plate to the beaker to the water, and therefore it is heat. It's moving from one place to another. Heat, when it flows, always flows from higher temperatures to lower temperatures. This is generally true of all forms of energy. They flow from higher concentrations, or sometimes higher potentials, to lower concentrations of energy. Heat flowing from higher temperatures to lower temperatures is part of what drives all of our weather patterns on the planet. Hot air flowing from the tropics out towards the poles, and then also warmer water in the oceans circulating from the tropics towards the poles. Those things are driving forces in our weather patterns. Now, if two objects are in contact with each other and are different temperatures, then the heat will flow from the higher temperature object to the lower temperature object until they are equal. When they're equal, then they will both stay the same temperature. So for example, if I put a hot coffee out into my room, heat will flow from the coffee into the room because the coffee is higher temperature, the room is lower temperature. That will happen until they are the same temperature. And in theory, the coffee can actually warm up the room. But because there's a lot more material in the air in the room, it won't be very much. The coffee will change temperature a lot, and the air will only change temperature a little. And then when they come together, that will be the new temperature of the room. Right? So heat flows from higher temperature to lower temperature until those two objects or two locations are the same temperature. When we talk about anything in chemistry, but particularly when we talk about energy flowing into or out of something, it's really important to define the system and the surroundings. Right? The system is whatever we're studying or whatever equipment we're using, whatever experiment we're doing in the laboratory. Tomorrow your system will be water in a beaker. So we're studying the water, and that's a very narrow, very specific system. The surroundings would be everything else, right? Which in the lab would include the beaker, would include the hot plate, the air in the room, anything else that's around the outside of that. I mean, theoretically, everything else in the universe, but of course, in practical terms, we mean the immediate surroundings around it. So air is often the surroundings. Going back to my body, the example of my body and losing heat when thermal energy flows out of my body and into the air. My body would be the system, and the air would be the surroundings. Sometimes environment could be used as surroundings as well. Right? And since my body temperature is higher than the temperature of the air, then the energy will flow from my body into the air. Okay? Now that's why it's very dangerous if it's hotter than body temperature outside, because our bodies are set up to lose heat, and when we don't lose heat, it can be very dangerous for us. Luckily, we can sweat, and that helps the process. When we talk about energy flowing into or out of something, we have terminology for that. When energy flows into our system, whatever it is we're studying, then that is said to be endothermic. Endo means into or inside of, right? And so thermal energy flowing into something. Or in other words, the system is gaining heat. Energy is going into the system. That means the surroundings are losing heat, right? So if I put ice water out in my room, then the ice water will be endothermic. Heat will flow from the hotter air into the colder ice water, as the water warms up in temperature. And of course, the ice has to melt too, and that's part of what we're talking about here is phase changes from one state to another, and that's what we'll be heading towards later in the week. All right, so endothermic systems absorb heat. All right, they'll feel cold to the touch because they absorb heat from you. All right, so when ice is melting, it's endothermic. All right, it's absorbing heat from its surroundings. If I put my finger on the ice, it's going to feel cold because it takes heat out of me and the heat goes into the system. When something is endothermic, its delta T will be positive. Right? We talked about delta T in Monday's lecture. That's because if I'm putting heat into it, the temperature will go up. With one exception, and I've mentioned that exception, we'll come to that eventually. Exothermic means the system is losing heat, so heat is flowing out of. Exo means out of or outside. Okay? And so exothermic systems lose heat to the environment, and the surroundings gain heat. So my coffee cup example was an exothermic system. The hot coffee, heat flows to the colder air around it, and so the coffee loses heat and the air gains heat, right, until they reach the same temperature. Now, the rate at which heat flows can change over time. So if I have really hot coffee in a cold room, heat's going to flow very rapidly between the two of them at first. As they get closer in temperature, the heat will actually slow down, and it will flow gradually. And so the curve flattens out a little bit if we're mapping the temperatures of the two of them. Exothermic systems will feel hot to the touch because you gain heat from them. They're giving off heat, right? So a stove burner is exothermic, right? It puts heat out into the air. The burner loses heat and the air gains heat. And whenever it's exothermic, if the temperature is changing, it doesn't always, when the temperature is changing, the delta T would be negative. Right, so that's a quick study of gaining and losing heat. And that brings us to states of matter, because that's what we want to talk about. We want to talk about the role that energy plays changing between these states, solid to liquid, liquid to gas, or vice versa, gas to liquid, liquid to solid. All right, now as I mentioned briefly at the end of Monday's lecture with our animations that I was showing you, the difference between our states has to do with the arrangement of the particles and with the freedom that they have to move. Right? So the key difference with liquid from solid is that the particles of the liquid are free to move around each other. The particles of the solid are not. They're locked in place. Right? Likewise, when we talk about changing from a liquid to a gas, the particles of the gas have much more freedom to move because they're separated from each other. And notice that the space between the particles is not the key determining factor between all three states, as is sometimes taught. Between solids and liquids, the space of the particles is not important at all. And in fact, in water, the liquid's particles are closer than the solid's particles. The space is only important in gases. When it comes to solids and liquids, the way we distinguish them is not by the space between the particles, but by the arrangement and freedom of movement of the particles. Right? And that's what defines the states. And so we can list all three states and talk a little bit about what we discussed briefly at the end of Monday's class in more detail. Solids have a defined shape and a defined volume, and those don't change unless I actually do something to the solid, like cut it into pieces. Right? A solid's not going to change its shape unless I do something to change it. A solid's not going to change its volume unless I do something to change it. And for most solids, you can't even like squeeze them into smaller spaces. Solids typically arrange themselves into patterns. There's a structure to a solid. That's not 100% true, but generally speaking it is. And in fact, the patterns and arrangement of particles in a solid is an entire science unto itself, which is something that we're not going to get into. It's very detailed. Solids cannot be compressed or squeezed. The particles can't get closer together because they're already very crowded. So there's very little space between the particles. There is some because spherical particles don't fit together perfectly. So there will always be a little bit of space between any particles in any state, solid, liquid, or gas. But in gas, that space is much larger and makes gases very different from solids and liquids. Because there's very little space between the particles, you can't really move the particles any closer together. Okay? Solids have particles that are locked together and they're not free to move. They cannot translate. They can't move around each other. And because of that, they have the lowest kinetic energy of any of the states. Their particles move the least. Liquids also have a defined volume. So the volume of a liquid doesn't change unless I do something like pour some of the liquid out. If I take a 1 liter bottle of soda and then pour it into an empty 2 liter, it will only fill it halfway because it's still 1 liter of liquid. It doesn't change its volume when I change the space around it or change the container available to it. So liquids retain their volume, but they do not retain their shape because their atoms and molecules are not arranged into a particular pattern. There's no structure anymore. So the main difference between solids and liquids is that the structure of the atoms has been broken apart, and now the atoms or molecules are free to move around. But again, liquids still cannot be compressed very much because in a liquid the particles are still close to each other. There's very little difference in the spacing of the particles between solids and liquids. And so with the particles still crowded together, we can't really squeeze them any closer to each other than they already are. So liquids have particles that are close together and crowded, which limits their movement, but they have more freedom to move than solids do. So I often say that like solids are like people marching in formation. You have a specific place and you stay in your specific place and everybody moves together with everybody staying in their rigid structure. Liquids are more like people moving through a crowd, like moving through a crowded hallway. And everybody can move, but you can't necessarily move very fast because there's a lot of people around you. You would bump into people very often if you try to move too fast. On the other hand, gases, the particles can move almost essentially as fast as they want to because they have a ton of space. Gases have an indefinite volume, which means their particles can spread out as much as they're allowed to. If I take a small container of a gas and open it, those particles will spread out, they'll fill the entire room. Which is why you can smell things in other parts of the house when they're being cooked in the kitchen. The particles of the gas spread, and they will occupy whatever volume they're allowed to. In other words, gases take the volume of their container as well as the shape of their container. Their volume and their shape can both change. Gases and liquids can both flow, and the general term for that is fluids. Okay? Anything that is a fluid can flow. It can be poured. It can move from one place to another. Solids generally don't flow. Some people think about like salt, sugar, sand, like you could technically pour them, but we're thinking more about one piece of a solid, one solid object, rather than a lot of pieces of a solid here. Gases can be compressed. In fact, they're highly compressible because there's a lot of space between the particles. And since there's a lot of space, I can squeeze them together into that space. If I squeeze enough, though, I will actually condense it back to a liquid. That's something that we'll talk about in the next unit. So gases have particles that are far apart. They have complete and total freedom to move. They can move wherever they want to and at pretty much any speed that they want to. And that's what makes gases very different from solids and liquids. So during this unit, we're going to focus on solids and liquids, and we'll save the gases for the next unit, Unit 3. All right, so that's the brief run-through of states of matter. If you have any questions, please let me know, and you can certainly ask them when you come to class during the lab. This will help you with some of the concepts in the lab, and there's one more set of notes for after the lab called phase changes. So make sure you're keeping up with the notes. Even though you're not doing the work in the packet right now, these notes do apply to next week's work in the packet. All right, and so no skipping over them. It's important. Of course, if you're skipping over it, I guess you didn't get that message. Anyway, have a good day. Stay safe, get some rest. I'll see you in lab this week.